Hey everyone, and today we're going to be doing two quick asymptote problems. Just going to be constructing some asymptotes from some descriptions, so let's get to it. Number one is write the equation of a function such that has asymptotes at y equals 4 and x equals 1 and a whole at 3, 5. So what do we need to do? First thing we know is that we have a whole at 3, 5. So the first thing we can do is plug x minus 3 into both the numerator and the denominator because that'll cancel us out. Now we also know that we want an asymptote at x equals 1. In order for that to be the case, we need x minus 1 in the denominator because with this, x minus 3 and x minus 3, they will cancel out. We will have 1 over x minus 1. And because of that, we can have an asymptote at x equals 1. Because you plug in 1, you get 0. It's the asymptote. Now the problem comes that we need to, 1, make the whole at not just x equals 3 and then any y coordinate, but we need it to be at 3, 5. And we also need a horizontal asymptote at y equals 4. So how do we do that? Starting with the horizontal asymptote, the way we do this, there's a few ways. And it all depends on the powers of the numerator and the denominator, or the degree. So essentially, right now we have x minus 3 over x minus 3 times x minus 1. So the power or the degree of the numerator is 1, whereas the power or the degree of the denominator is 2. What this means is the horizontal asymptote is not happening at y equals 4, because when we have a lesser power divided by a greater power, it'll just happen. I believe it's just at y equals 0, so it'll just tend to 0 as x goes to infinity. And then the other two cases are when the degrees are the same, which is what we want in this case, meaning when the degrees of the numerator and the denominator are the same, the horizontal asymptote occurs at the ratio of the two leading coefficients. So if I were to add another x in here, just x, now the degrees are the same. However, if we were to expand this all out, it would just be the leading term would be x squared, and the coefficient of x squared is just 1. The bottom term would also be x squared, and that also has a coefficient of 1. So what we really need is a 4. So let me get rid of this x. Let me put parentheses, we want a 4x. And now what we can do from here, I'm not going to close the parentheses because I know the answer to this problem, but from here we can actually try to test this out. So we cancel these, we have 4x over x minus 1. And what we're testing for is to see if the whole occurs at the point 3, 5. So we plug in 3 to both numerator and denominator, we get 12 over 3 minus 1 is 2. So of course this comes out to 6, which does not equal 5. So what's this mean? Well, we want the numerator to decrease, or the denominator I guess, but it's easier for the numerator to decrease in such a way that when divided by 2, we get 5. Of course, that just means we want 10 over 2, not 12 over 2. So we can just slap in minus 2, slap in a minus 2 over here, and here we go. This is our full equation, so we have the full thing as x minus 3 times, not x, but 4x. So we want 4x minus 2, and this is all over, once again, x minus 3 to give us the whole at x equals 3, and then x minus 1 to have a vertical asymptote at x equals 1. These x minus 3's will cancel out. We will be left with 4x minus 2 over x minus 1, and when we plug in 3 to that, we will output 5, which confirms that our whole will be at 3, 5, and we still have our vertical asymptote at x equals 1. So that's all great. I think I can I never know how to use this stupid. I'm just gonna erase. That is way faster. Okay, so that's our first equation. Probably should have wrote the answer up here. So we'll have x minus 3, 4x minus 2, and this will also be x minus 3 and x minus 1. Of course, if you don't believe me, I guess you could check for yourself that it does check these boxes for the asymptotes in the whole. Now let's move on to the second one. It states, write the equation of a function such that has an asymptote at x equals 1, no horizontal asymptote, and holes at 2, -1, and -2, 1. So this one is a little bit tougher, but we can start with the same approach. So we want holes at 2 and -2. So that means we're automatically going to have an x minus 2 and an x plus 2 on both the numerator and the denominator. We'll worry about how we'll get it at -1 and 1 afterwards, but first I just want these. Next up, we want an asymptote at x equals 0, so we just want put the x out here, just an x. So when these all cancel out, it'll simplify down to 1 over x, which of course has a vertical asymptote at x equals 0. Now the big part is there's no horizontal asymptote. What this means, as I stated earlier, or well, I didn't state earlier, but the third case for asymptotes is when the numerator's degree is greater than the denominator's. What results then is just an application of polynomial division, where you can simplify things out, and the asymptote, instead of being a vertical or a horizontal asymptote, is something more in between. It's called an oblique asymptote or a slant asymptote. Essentially, it's the result of dividing polynomials. You get a simpler polynomial that you can then graph the line of, and that's what the asymptote follows. So what that means for us is we need a degree in the numerator that is greater than the degree in the denominator. The denominator's degree currently is 3, because if we multiply this all out, we'd have a leading term of x cubed, whereas on top we have a leading term of x squared. So if we add another x, it'll be the same power, which is not what we want, so we are going to add an x squared. And we're going to add an x squared. What does this mean for us? If we cancel all these out, we will just have x squared over x. And now if we plug in -2 and 2, I'll do at x equals 2, our function equals, well, plug in 2. 2 squared is 4 over 2 is, well, 4 over 2, which is 2, which is definitely not equal to -1, which is where we want the hole at. Similarly, at x equals -2, we still get 4, but this time it'll be over -2, which gets us -2. It's not equal to 1. So what do we need to do? Well, for 1, we have the 4 over the 2. However, we don't want that. We want 2 over 2, because ideally that does simplify down to 1. So first, we're going to subtract 2 here. I'm going to subtract 2. That is a... oh, wow. Okay. That's a mildly better looking 2. So now we have x squared minus 2. So let us shift this way. So now I'll write it up here. So now with x squared minus 2 over x, we can now plug in our 2's again. And what will that do? So at x equals 2, we get 2 squared, 4 minus 2 is 2 over 2, which is 1. Which, while that does not equal -1, which is what we want, it is a lot closer. Similarly, at x equals -2, not -z, -2, we get -2 squared, which is still 4, minus 2 is 2. Now it's over -2, which is equal to -1, which is not equal to 1. So now all we have to do is swap the signs. There are a few ways you can do this, but I think a more interesting way that results in a sort of a cooler looking graph is we look at it like this. We need essentially these signs for our answers to be swapped. So the first thing we're going to do is we're going to add an absolute value or add a negative sign. This is very much not necessarily needed. You could add just the negative sign down to the bottom, because x squared minus 2 for all x is going to be positive anyway. At least all real number x's, it's going to be positive anyway. So this is a more out there answer. You could just add a negative sign to our x here. But with this new function, we're going to evaluate it down here. So at x, I forgot the x equals 2. We get 2 squared. Once again, 4 minus 2 is 2. But then we have negative 2 over 2, which is in fact equal to negative 1. So we got our first whole. And now at x equals negative 2, negative 2 squared minus 2 is still 2 over, but then we add the negative sign from the absolute value, so we get negative 2 over negative 2, which comes out to positive 1, so we have our second whole. So this is the actual term we need, namely the absolute value, or negative absolute value of x squared minus 2. That is not necessary. You could just add the negative to the x in the denominator, but I think it makes for a cooler looking function, so why not? So ultimately we need negative x squared, or sorry, negative absolute value of x squared minus 2 times our x minus 2, x plus 2. This will all be over x times the same thing, x minus 2 and x plus 2. And this does in fact satisfy all our requirements for our wholes and our asymptotes. And yeah, thank you for watching.